All right, let's dive in. Today, we're tackling a classic algebra challenge that can feel a little tricky, the exponential equation. We're going to demystify the whole process and hand you the keys to solve for a variable when it's kind of trapped up there in an exponent.
So this is the big question, right? You're looking at an equation, the variable you need to find is the exponent, and all your usual go-to algebra moves just don't seem to work. It's a super common place to get stuck, but I promise, by the end of this, you'll see it's totally doable.
Let's just look at a real example here. 2 to the power of x equals 20. Okay, we know 2 to the 4th power is 16, and 2 to the 5th is 32. So whatever x is, it has to be somewhere between 4 and 5. But how do we get the exact number? That's the puzzle we're about to unlock.
So, here's our game plan. We'll kick things off with the simplest method out there, finding a common base. Then, we'll bring out the master key for the trickier problems, logarithms. After that, we'll talk about a few common mistakes to watch out for. And then, the fun part, we'll see where all this math actually shows up in the real world.
Okay, our first tool is the most direct one, the common base method. And when you can use this, it's awesome. It feels like you have the perfect key that just pops the lock right open.
This right here is the rule that makes the whole method work. It's called the one-to-one property, and honestly, it's pretty simple. It just says that if you can make the big numbers on the bottom, the bases, the same on both sides of the equation, then their exponents have to be equal. It's a fantastic shortcut.
And the process is just a simple 3-step recipe. First, you've got to find that common base and rewrite your equation. Second, once the bases match, you can literally just set the exponents equal to each other. And from there, it's just a regular algebra problem you already know how to solve.
Okay, let's get our hands dirty with an example. So, at first glance, the bases look different, right? We've got a 3 on one side and a 9 on the other. But you can probably already see the connection here. And that's our first move. We all know that 9 is just 3 squared. So by swapping that in, we've done it. We've rewritten the equation so that both sides have that same beautiful base of 3.
Now we just use our rules for exponents. That 2 gets distributed, so it multiplies both the z and the 5. That leaves us with 3 to the power of z equals 3 to the power of 2z plus 10. And now for the best part, that one-to-one property lets us just drop the bases and focus on the simple equation, z equals 2z plus 10. A little quick algebra, and we find out z is negative 10.
Now, the common base method is great, but let's be real, it doesn't always work. For those tougher locks, we need a master key. And that key, my friends, is the logarithm.
This takes us all the way back to our very first problem. 2 to the power of x equals 20. There's just no nice, clean whole number we can use for x here. You can't rewrite 20 as a simple power of 2. So that common base method, it's a no-go. So what do we do now?
We pull out the tool that was literally invented for this exact problem, the logarithm. All a logarithm is really is an exponent. It's the reverse of an exponential, and it's designed to answer one question. What exponent do I need to get from this base to that number?
This chart shows it perfectly. They're just two sides of the same coin. Saying 10 squared equals 100 is the exact same thing as saying the log base 10 of 100 is 2. They're just two different languages for saying the same thing.
And the process for using logarithms is just as methodical. First, get that exponential part all by itself. Then, take the log of both sides of the equation. After that, you use a really cool trick called the power rule to bring the variable down out of the exponent. And then, you just solve for it. So, back to our original problem. The exponential part, 2 to the x, is already isolated, so we can jump right to step 2. We're going to take the natural log of both sides. You'll see it as ln on your calculator, and it's the one we use most of the time. And this is the magic step. The power rule of logarithms lets us take that x that was stuck up in the exponent and just move it down to the front as a coefficient. And just like that, the variable is free. We've turned it into a simple equation we definitely know how to solve.
So, we've solved it. To get x by itself, we just divide the natural log of 20 by the natural log of 2. You punch that into a calculator, and there's our answer, approximately 4.32, which, remember, fits perfectly with our first guess that the answer had to be between 4 and 5.
Okay, now that you've got the keys, let's make sure you're using them the right way. It's really easy to make a few common slip-ups when you're solving these, so let's walk through what to avoid. This is absolutely crucial. It doesn't matter if you're using common bases or logarithms, you must isolate that exponential term first. That means you've got to deal with any other numbers being added, subtracted, or multiplied before you even think about tackling the exponent.
Here are 2 classic mistakes you'll see all the time. First, forgetting to distribute correctly. In our earlier problem, that 2 times the quantity z plus 5 has to become 2z plus 10, not 2z plus 5. The other big one is taking the logarithm way too early. You have to get that exponential part alone first. In an equation like this one, you've got to add the a to the other side and then divide by 5 times before you can take the natural log.
So, why does any of this matter? Where does this math actually pop up in real life? Well, it turns out exponential equations are the language we use to describe some of the most powerful kinds of change in the entire world.
What do you think this number represents? It's the result of a really powerful force working its magic over time.
That number? That's what you get if you invest $10,000 at 5% interest, compounded continuously for 10 years. Exponential equations are behind finance. They're used to model how populations grow, how we use carbon-14 to date ancient fossils, how we measure earthquakes, even how risk is calculated. This math is quite literally all around us.
So there you have it. You now have the tools to understand and solve for patterns of really rapid growth and decay. You can finally unlock those variables that seemed trapped forever. So the only question left is, what problems are you going to solve?